Hello, everyone. Do you believe that you can sculpt your own brain? Can you picture your brain forming new connections as you meet the challenge and learn? Hopefully, you will by the end of this neuroplasticity and learning screencast. Let's begin by busting some myths. We use only 10% of our brain. True or false? The answer is a resounding no. False. This is one of the most pervasive myths in neuroscience. We use 100% of our brains. When a brain region is damaged, other parts of the brain can sometimes take up its function. True or false? This is true, and it gets to the core of the concept of neuroplasticity. For example, when somebody has a stroke, other non damaged brain areas can sometimes restore movement or language functions. Individuals learn better when they receive information in their preferred learning style. For example, auditory, visual, kinesthetic. True or false? False! You may be surprised at this answer, but this is another pervasive myth in psychology and neuroscience. The brain is a highly integrated machine that favors multimodal learning and intersensory redundancy. In other words, you may prefer ice cream, but you also gotta eat your broccoli. Lastly, learning occurs through modification of the brain's neural connections. True or false? True, as we shall see next. The founder of neuroscience and 1906 Nobel laureate Santiago Ramon y Cajal once famously said that any person could, if he or she were so inclined, be the sculptor of their own brain. This is a noteworthy and highly empowering quote. Would you agree? Neuroplasticity, therefore, is the brain's capacity to adapt and remodel itself, both structurally and functionally, in response to environmental experiences. Unlike previously thought, we now know that this happens throughout life. What are some examples of neuroplasticity? Think of the musician, pianist or cellist in this case, practicing away their skill for hours. What is going on in their brains? As they acquire this skill, the motor areas in their cerebral cortex are responsible for controlling fingers are becoming thicker. How about the cabbie, riding around town, accurately getting to specific destinations upon request? This particular study was conducted before widespread GPS navigation. Researchers took MRIs of the brains of London cab drivers who have to study extensively in order to learn the city's grid. They found that cabbies displayed larger posterior hippocampi, an area associated with memory and spatial navigation, compared to controls, and the extent of this difference correlated with the amount of driving experience. So that's neuroplasticity in action. But how exactly does the brain change as a result of experience? What is actually going on at the cellular and molecular levels? You can see here a neuronal connection, a synapse, portrayed here on the left-hand panel, illustrated on the left-hand panel. And this will guide us as we understand what neuroplasticity is at the cellular and molecular level. So, how does it happen? Well, synapses, or connections between neurons, are being strengthened or weakened, and myelin is being thickened or thinned around axons. Think of this as laying down electrical cables and insulating them so that energy or neural signals can travel faster and more accurately. Or, say, like building roads and highways and allowing traffic to flow smoothly. There is also chemical efficiency. This flow of electricity eventually, as we know, after the action potential becomes a chemical event with the release of neurotransmitters that will then bind to receptors on the other side. This neurotransmitter release becomes more efficient with either more receptors being built to take up the same amount of neurotransmitter or more neurotransmitters being released in order to send a more accurate and effective message. Remember though, even though my previous examples all had a positive outcome, as in skill acquisition, neuroplasticity is not good or bad. It is pure adaptation. Research with rodents is able to provide an even greater level of detail at the molecular level. As we can see here in this study, following training with either a sensory or a motor task, illustrated here on the left-hand panel, transcranial photon imaging reveals the difference in the number of dendritic spines before and 2 days after the motor learning task in particular. Can you see the difference? The extent of the alteration of the dendritic spines also correlated with the behavioral improvement after learning, as in the cab driver experiment. To conclude, let's leave you with some insight into the learning process in general and a few practical tips to help you improve your own learning. So, how do I learn? I learn if I feel okay. That is, I sleep adequately, I exercise my body, and I am mentally and emotionally healthy. I learn if it matters. That is, if it's relevant to my life. If it's active, experiential, hands-on. If I wrestle with it. That is, am I provided challenges that are achievable? If I have a coach, if I have guidance throughout the process. If I have to use it, am I using what I'm learning? Is it useful? If I think back on it. I learn if I allow myself opportunities to review, integrate, and make connections with other stored knowledge. So keep that in mind as you go and learn and you meet the challenge. Now that you know, can you understand the concept of neuroplasticity and provide specific examples? Explain the cellular and molecular mechanisms of neuroplasticity? Apply neuroplasticity to learning, your own learning? See you next time, everyone.